are the cosmos' most recent episode in a multi-billion-year story. You exist thanks to your parents, who exist thanks to your grandparents, who are preceded by your great-grandparents, and your great-great-grandparents, and your great-great-great-great-great-grandparents. Before that, your ancestors, the first of the Homo sapiens, lived in either Eastern Africa or the Middle East. Earlier still, your ancestors were apes reminiscent of the gibbon. Before that, your ancestors lived in trees as monkeys with tails. And before that, now 80 million years ago, they were small, nocturnal, insect-eating mammals with tails called the Euryconta. Before that, they were this weird rat-pig combo called Juramea sinensis. And 250 million years ago, they were this evil 5-foot-long lizard. 300 million years ago, our grandparents were tiny little lizards. And 365 million years ago, they were these long, blue fish-frog hybrids. Before that, we go back to our original home, the ocean, as fish. Before fish, eels. Before eels, sea cucumbers. 900 million years ago, our living ancestors were choanoflagellates, one of the first beings to sexually reproduce. Then it gets sketchy. 2.1 billion years ago, prokaryotes, complex cells, emerged, and 2.5 billion years ago, the first prokaryote-like organisms to use oxygen existed. But what was before that? What did our first ancestor look like? And how did life come to exist on Earth? The Russian biochemist Alexander Oparin suggested one chain of events for the origin of life. His idea was that simple molecules led to molecules of life, which led to macromolecules, which became polymer complexes, which became metabolic networks, which finally became living cells. But while it sounds like a good idea, it wasn't testable at the time he thought of it, and thus it wasn't a real scientific theory. Currently, the general opinion of scientists is that life is created in a primordial soup. Not the cosmological type of primordial soup, but the astrobiological type, meaning a soup of amino acids and sugars in a body of water here on Earth billions of years ago. With that said, organic molecules have been discovered on asteroids and other extraterrestrial objects, which leads some scientists to believe that the ingredients for life came from somewhere else in the universe. Still, we'll stick with the hypotheses for life developing on Earth, as they're generally more heavily supported by science. Let's take a look at some of those ideas. One idea scientists have is that metabolism was the first way life developed. If we go back to Oparin's proposition, he was one of the people who think that metabolism came first. This would mean that the ability to break down carbon dioxide into small organic molecules was the first capability of life, and that genetic molecules, genes, somehow developed later on. There's a number of different theories as to what specific molecules and catalysts would have made up those early systems of life. Alternatively, some scientists think genes were the first signs of life on Earth. That means single molecules, genes, developed which had the ability to autonomously drive the replication of their own traits. This seems fairly likely, as simple systems like crystals and viruses have been proven to be able to evolve with certain traits that breed true. Perhaps most interesting and developed, however, is the RNA world hypothesis. This is the idea that all living things originated from RNA, before DNA existed. Pools of liquid on the early Earth would chemically form random chains of RNA molecules. RNA molecules, which are abundant in every form of life and are a close chemical cousin of DNA, are comprised of chains of nucleotides, which are even smaller molecules. There are 4 types of nucleotides, labeled A, C, U, or G. Those nucleotides will pair with other nucleotides, but only certain types. A will only pair with U, and C will only pair with G. This allows RNA to effectively reproduce. So, for example, if we have a 4-nucleotide of AAGC, and it's placed in a soup of loose nucleotides, it'll create a bond with an inverse chain, in this case, UUCG. But then, if the temperature of the water is changed, those 2 chains will separate. Then, the cycle repeats. Those 2 chains go pair with other inverse chains, replicating and driving their species' survival. Moreover, mutations can happen when they split, which introduces the element of competition for survival and evolution. Then, it gets interesting. Sometimes RNA chains will incidentally bond with themselves, which causes weird shapes in the chains and leaves certain nucleotides bare and exposed. These molecules, called ribozymes, can use their exposed nucleotides to perform an action, perhaps breaking apart molecules or joining two molecules together. Sometimes, and this is important, these ribozymes are able to create nucleotides themselves. Since nucleotides are crucial for RNA's multiplication, the ribozymes that can create nucleotides might survive longer than those that can't. Now we have molecules that can catalyze their own survival, which serves to blur the line between chemistry and life. While some aspects of this theory are still being developed, and there are some issues with the natural formation of RNA chains, it does show a lot of promise. In 1952, Stanley Miller and Harold Urey worked together on a new science experiment. They wanted to see if, with the natural conditions and materials of the early Earth, life could have formed from non-living objects, which simultaneously tested the first step in Alexander Oparin's predicted chain of events. To test it, they set up a contraption that would replicate the atmosphere, temperature, and water cycle of the early Earth. It had a chamber of the gases that they believed filled the early Earth's atmosphere, a heat source to replicate the temperature of the Earth and cause evaporation, a spark generator to simulate lightning, a condenser to make simulated rain, and a pool of water to recreate the ocean or tide pool that they believe life may have formed in. Much to their surprise, in about a week, their ocean became filled with complex molecules, some of which were organic. That included amino acids and, especially important, nitrogenous bases. This was huge. Nitrogenous bases are the primary ingredient in nucleotides, the things that drive the reproduction of RNA and DNA. Moreover, the Miller-Urey experiment proved not only that components of life can form under the circumstances of the early Earth, but that they automatically do. Now, that first step in Oparin's chain of events was finally testable, and it was proven true. Lastly, scientists aim to understand the organism that they call LUCA. It stands for Last Universal Common Ancestor, and was the organism that every single living being on Earth descended from. LUCA is similar to dark energy in that it's a placeholder name for something we don't entirely understand. Still, she helps us understand the path of the evolution of life, all the way down to ourselves. For example, we know that LUCA lived at least 2 billion years ago, likely the direct ancestor of bacteria and archaea. We also know that she lived underwater and that she used RNA. Beyond that, our search for what our common ancestor looked like is still ongoing, but we're still making progress. The search for the origin of life opens some interesting philosophical speculation. Firstly, what even is a living thing? Biologists classify life according to a checklist of attributes, including heritable reproduction, evolution, metabolism, and movement. But, at its core, every living thing is simply a bundle of chemical reactions all working towards a common goal: survival and reproduction. More basic still, we're just one big molecule of atoms. That is, one big molecule of atoms who are all working together to find out how the first living molecule came to be.